Good afternoon, morning, some time of day. Um, Today is Thursday, June the 4th, and today we are going to talk about the idea of uh, modern physics once again. Um, but this time we're going to add to it a discussion of nuclear physics, right? You'll recall from the previous video that we talked about the electrons and the amount of energy that they gave up or absorbed as they moved from orbital to orbital. Today, we're going to concentrate on the nucleus, and this plays a huge role in today's scientific expansion because nuclear physics is the wave of the future. All right, we keep talking about renewable sources of energy and all that kind of stuff. When in reality, we have a source of energy that is absolutely astounding, sitting around us all over the place, and that is, of course, in terms of nuclear physics. Now, what do we do? What do we talk about in terms of nuclear physics here? Well, first of all, what is the nucleus of an atom? All right, we're not talking about a cellular nucleus now, but the nucleus of an atom. All right, every atom has a nucleus. And in that nucleus is some combination of protons and neutrons. Hopefully, you remember this from Mr. Leonard's chemistry class. All right. But essentially, the nucleus is simply the center of the atom. And this is where the most of the mass of the atom exists. All right. The electrons, remember, are essentially massless. All right. They're very, very small. And so, therefore, the protons and neutrons in the nucleus contain most of the mass of an atom and all of the positive charge. Right now, obviously, the positive charge goes with the protons because the neutrons are neutral, right? They have no electrical charge. More on that in the next lesson, all right? Now, together, these two types of particles make up what we call the nucleons, all right? These are the particles that you find in the nucleus. And of course, we said already that these are the protons and the neutrons. Now, because protons and neutrons have most of the mass, that means that the nucleus contains most of the mass. All right. Now, when you describe an atom, you typically use two different numbers to describe it. The first one is what we call the atomic number. And this is what identifies an atom as an atom of a specific element. And it is simply the number of protons that are found in the nucleus of that atom. Now, all hydrogen atoms have one proton. All heliums have two. All lithiums have three, and so on. Carbons have four. Oxygens have eight. Sodiums have 11. Chlorines have 17. That's what makes them chlorine or sodium or hydrogen or whatever they happen to be. However, because the protons aren't the only particle found in the nucleus, we also have to add the number of neutrons in the nucleus in order to get the atomic mass. Now, hopefully you recall from Mr. Leonard's class that the atomic mass is not exactly the number of protons and neutrons. There's also a small fraction there. When you looked at the atomic mass on the periodic table, you never saw, 4 or 12 or, 978, whatever it was. All right, you saw a whole number with a decimal that came after it. And this is important, all right, because those fractions actually do play a role in what we've got. More on that in a second. So one of the things that I do want to talk to you about is something that Mr. Leonard probably never talked to you about. We learned in the electricity unit that if you have two positive charges that are near one another, they repel one another. There's an electrostatic force between them that tries to force them to move apart. The nucleus of an atom contains only neutral positive particles and positively charged particle. So what exactly is holding the nucleus together? In reality, all right, based on what we learned in electrostatics, every nucleus in the universe should blow apart immediately, all right, because all of those positively charged protons should be repelling one another. Well, this is where nuclear physics comes in. There is a force called the nuclear force, and this is really only the third universal force that we've talked about. Okay, the nuclear force is a force of attraction between protons and neutrons in the nucleus of an atom. Now, it's huge. It's got to be huge because the electrostatic force would force the protons to fly apart. And so it turns out that the nuclear force is about 100 times greater than the electrostatic repulsive force. But it acts only over very, very, very small distances, short distances here. All right, so it's 100 times greater than than Coulomb's force, but it acts only over very tiny distances, like, for example, the diameter of the nucleus of an atom. Okay. Now, what does that then lead us to? Well, let's go back and talk about the masses of each of the particles that you find inside an atom, not just the nucleus, but an atom as a whole. All right. Back in the old days, we used to say that each proton and each neutron had a mass of 1 atomic mass unit. Okay, and 1 AMU is equivalent to 1.67 times 10 to the negative 27th kilograms. So it's a really tiny particle. Okay, now it turns out that a proton does not really have a mass of exactly 1 AMU. It turns out that a proton has a mass of 1.0073 AMUs. Okay, so it's a little bit bigger than you might expect. 1 neutron is even bigger than that. Not very much, but even bigger than a proton. It's got a mass of 1.0087 AMUs. Finally, the mass of 1 electron is 0.0005 AMU. So it's exceptionally tiny, even compared to a proton or a neutron, which is why we can get away with saying that an electron has no mass, because in reality, its mass is insignificant compared to the mass of one of the nucleons. Now, Einstein, Joe Einstein, realized that there was a relationship between mass and energy. And you know this formula. You've seen it before, all right? Probably not in physics, but certainly in common life, all right? The mass-energy relationship is E equals mc squared. Now, this formula, by the way, is found on your handy-dandy reference tables. It is the third and final formula in the modern physics box. So make sure that you have that ready for you. And of course, always realize that the list of physical constants is an important aspect as well. The rest masses of all of those subatomic particles are given on the bottom there, all right? The rest masses of protons, neutrons, and electrons, okay? As well as some other useful information. So how do we actually use this formula? Well, let's do an example, shall we? So example number 7 for this unit. In this case, you're asked to find the energy equivalent of 1 AMU in millielectron volts. Now, I'm going to tell you right off the bat that you could actually go to the front page of your reference tables and look this up. But I'm going to show you how to actually derive it. All right, so find the energy equivalent of 1 AMU in mega electron volts. So what do? Well, we know that 1 atomic mass unit is equal to 1.67 times 10 to the negative 27th kilograms. All right, so there's my mass value. All right, and I can look that up just by going to my reference tables, and there it is. All right. Now, using the formula E equals mc squared, I can now plug and chug. All right, I've got 1.67 times 10 to the negative 27th, and I'm going to multiply that by 3.0 times 10 to the 8th meters per second squared. If you do the arithmetic, get out your magic number box and actually do the math here, you'll find that this calculation gives you 1.50, and I'm estimating here, I'm rounding off, times 10 to the negative 10th joules. Okay. Now, that doesn't answer the question in terms of electron volts or even mega electron volts. So what do? Well, I go to my reference tables and I find on the list of physical constants that the 1 electron volt, where is it now? There we go. 1 electron volt is equal to 1.60 times 10 to the negative 19th joules. Okay, so if I take this number and I multiply it by 1 electron volt over 1.60 times 10 to the negative 19th joules, and I do the arithmetic there, I get an energy value, E, of, what does it come out to be? 9.39 times 10 to the 8th electron volts. Okay. Now, if you recall, the question asked actually for the answer to be in mega electron volts. And if you don't remember what mega is, go back to your reference tables, and the prefixes for power of 10 are here. Mega is right there. It's 10 to the 6th. Okay. And so if I remove 10 to the 6th from here, I get an energy value of 9.39 times 10 to the 2th mega electron volts. And so there is my answer. All right. Okay. So that's the amount of energy that's available in 1 atomic mass unit of mass. All right. That's a lot of energy for such a tiny little bit of mass. But whenever you square something that is 10 to the 8th power, you're going to get a huge number here. Okay. Now, why is this important? Why do we need to know that you can convert energy to mass, or mass to energy, and get a tremendous amount of energy from just a teeny tiny bit of mass? Well, this is the principle that runs nuclear reactors and, unfortunately, nuclear weapons as well. All right, you can get a tremendous amount of energy from just a couple of pounds of uranium or plutonium or neptunium, any of these radioactive elements that give off alpha particles. Well, the next question then is, why is that? Well, it turns out that in terms of nuclear physics, there's a mystery involved. Okay, a helium nucleus. All right, helium is element number 2 because it contains 2 protons, and it also happens to have 2 protons, and it happens to have 2 neutrons as well. And if you add up all of those masses for 2 protons and 2 neutrons, you should come up with a total of 4.0320 units. However, a helium nucleus actually has a mass of 4.0016 units. Where is the missing mass. Where does it go? We call it, by the way, the mass defect. But it's gone. It's missing. It doesn't. There's no trace of it anywhere. Well, it turns out that this missing mass is converted into what we call the binding energy of the nucleus. It holds the protons and the neutrons together in what we call the strong nuclear force, which I remember we said just a few slides ago was 100 times greater than the electrostatic force of repulsion that the protons are experiencing. All right, so that missing mass, the mass defect, is converted into the binding energy, which is the energy that provides the strong nuclear force. Now, that brings us to example number 8. Okay, and so here I'm going to ask you actually to find the difference between the mass of a helium nucleus and the total mass of its constituents, and to find the energy equivalent of this mass in mega electron volts. All right, so the problem is similar to the one that we did in example number 7, except that I'm going to ask you to start with the actual subatomic particle units. All right, so how do we do this? Well, we know that the mass of one proton,
it's 6 o'clock.
Thank you, Jesus, is equal to 1.0073. But there's 2 of them in a helium nucleus, which, by the way, is an alpha particle, if you remember that from chemistry. One neutron has a mass of 1.0087 atomic mass units. But again, in a helium nucleus, there are 2 of them. And so these 4 particles altogether give you a total mass of 4.0320 units. All right. Now, remember that in 2 slides ago, I told you that so this is the theoretical mass of helium, but the actual mass of helium, this alpha particle, is 4.0016 units. So we're missing a bunch of mass here. What's the difference here? Well, all you got to do is subtract these 2 numbers, and you get 0.0304. And so that number, 0.0304, is the mass defect here. Okay, this is the mass defect. Now, let's take that number and convert it to kilograms. So 0.0304, and I'm going to multiply it by what was the 1.67 times 10 to the negative 27th kilograms. All right, because that's the value of 1 electron volt. I'm sorry, 1 AMU here. And so if we do that calculation, we come up with 5.08. And again, I'm rounding all of these numbers, times 10 to the negative 29th. And of course, that's in kilograms. Now, that's a very teeny tiny little mass, all right? However, if I now take that mass and plug it into Einstein's equation, E equals mc squared, that's going to then be 5.08 times 10 to the negative 29th times 3.00 times 10 to the 8th meters per second quantity squared. Do the arithmetic there, and you end up with a value of energy as 4.57 times 10 to the negative 12th joules. Okay, and again, that doesn't seem like a whole lot of energy. But if I convert that back to electron volts here, remember 1 electron volt is equal to 1.60 times 10 to the negative 19th joules. I can look that right up on the front page of the New York State reference tables. And that gives me an energy value of 2.86 times 10 to the 7th electron volts. And now that seems like a more considerable number. Or I think the question asked for mega electron volts. So get rid of 10 to the 6th. It becomes 28.6 mega electron volts. All right, or 2.86 times 10 to the 1th mega electron volts. All right, so this is the answer. So that's the amount of energy that I get out of one helium nucleus. Okay, that's the binding energy of one helium nucleus. That's a lot of energy for one teeny weeny little nucleus. All right, and so this is a very important aspect here. Okay, now this brings us to our homework assignment, and this will be due on Friday, tomorrow, at the end of the day. And this will be numbers 8 through 9 on the homework sheet. Now, tomorrow, Friday, I would like to have a review activity on the first portion of modern physics. And so there, I'd like you to concentrate on the homework problems 1 through 4. All right, so it won't include 5 through 7 or 8 and 9, both of which are due tomorrow evening. All right, tomorrow morning, we'll have an activity on numbers 1 through 4. All right? All right. Gentlemen, happy Thursday, and I will see you sometime in the near future.